meteorology students, Dr. John Schrage here, and we're starting a new module of the class that's all about moisture and humidity and rain and clouds and so on. And so we're going to be talking a lot about water, and as a consequence we have to start off this module by talking about phase transitions of water. This is going to be all about, this isn't grade school science or something like that, but we're going to get a little bit into detail about like forming ice, forming liquid water, condensation, evaporation, all that kind of good stuff. To understand this business about phase transitions in water, let me tell you that what's going to happen is we're going to have to first talk about the very nature of the water molecule itself, because that's going to explain a lot about how evaporation, condensation, freezing, and so on all work. And then we're going to actually talk not so much about the phases of water itself, like ice and water vapor and liquid water, which, hooray, now you know them. We're going to talk about the transitions. It's really the transitions from one phase to another that has significance in meteorology. So we'll talk about melting and freezing, we'll talk about evaporation and condensation, and we'll talk about sublimation and deposition. But let's start off by talking about the nature of the water molecule itself. It's actually a really interesting molecule. You probably knew from like grade school science and high school science and so on that we usually draw it as sort of a Mickey Mouse shape, right? Where he's got two ears and he's got a big head. And that's because the molecule is H2O, two hydrogens and one oxygen atom chemically bound to make a water molecule. And it turns out that they're not, I don't know how you might have pictured it, maybe lined up like hydrogen, hydrogen, oxygen. In fact, the oxygen atom is bigger, and the two hydrogen atoms sit at about a 90-degree angle from each other at the top, on one side of the oxygen. It makes kind of a Mickey Mouse shape. That's why we tend to draw it that way. What's truly amazing, though, about water, the water molecule, is it's a very simple molecule, yet it is what is called a polar molecule. Here we're using the word polar not as in cold or from the Arctic or something, but in the sense of like like magnetic poles, okay? In this case it's actually electrical poles. Because of the distribution of electrical charges from the electrons around those hydrogen and oxygen atoms, we in fact end up with one end of the molecule that tends to be positive and one end of the molecule that tends to be negative. That's not a tremendously exotic thing for like a complicated chemical molecule made by DuPont Chemical, but it's a rather unusual thing for something that's one of the most abundant natural materials on Earth. As it happens, if you think about it as sort of Mickey Mouse shaped, the forehead of Mickey is positively charged and the chin of Mickey is negatively charged. And this property of being a polar molecule gives water most of its really unusual properties. Water is in fact a very strange material, but what we're going to be most interested in is how this material heats up and how it changes from solid to liquid to gas. Let's talk about heating up, how we heat something up. When you heat up an object, you add heat to the material, and that makes the molecules move around faster. It's actually the speed of the molecules moving around that is what we experience as temperature. Oh, if you're a survivor of the ATS 114 lab, you know that it's a little more complicated than that. It's the kinetic energy of them. Oh, I don't care about that right now. You add energy in the form of heat to the material, and the molecules move faster. And that's a really good rule of thumb as to how heating happens. But that's actually really hard when it comes to water molecules because of their polar nature. See, they tend to kind of stick to each other. Mickey's forehead is positively charged, Mickey Mouse's chin area is negatively charged. The opposite charges attract. The molecules kind of tend to stick to each other, and they tend to kind of be hard to pull apart. They make actually little chains of these molecules, and that makes them harder to get moving. And to kind of illustrate that point, I grab a box of my kids' Legos. Think of this as a sample of some material, and these Legos that are loose in here are molecules of something. I don't care. Oxygen, carbon dioxide, something other than water. If I apply some energy to this sample of oxygen, carbon dioxide, whatever, anything other than water, look, I'm hardly applying any energy to it, and I can hear them, they're moving around, right? Okay, it doesn't take that much energy to get them moving around. But water molecules are quite different. Instead, let me put the lid down here someplace. Instead of being loosey-goosey, just sort of flying every which way, they stick to each other. kind of like these Legos are sticking to each other. And if I just kept like putting them all together and making one stick to another and another one stick to another, like I guess here's a piece of an airplane or something, okay? They're sticking to each other. Now, like water molecules sticking to each other, these Legos are sticking to each other. Imagine that they were all stuck together like that. Now if I was, I mean, I'd have to, if I'm going to actually, I don't want to break my kid's airplane that's in there. If I actually was going to wiggle that thing around enough to make that airplane, all the little Legos that were in that airplane move different, I'd have to really shake the heck out of this box. I'd have to add a whole lot of energy to break the connections between all those Legos. And in the same way, if I'm going to heat up some water, I gotta first break all the connections between all those little water molecules because they're polar. They're sticking to each other. It's gonna take a lot of energy. In fact, it takes an incredibly large amount of energy. In fact, per kilogram of water or per gram of water, whatever, it takes a lot of energy. In fact, so much energy, it's actually one of the most amounts of energy to increase the temperature of any natural material. There's a few exotic materials like liquid helium and things like that that have a higher specific heat. We'll come to that word in just a second. But water's about as high as it gets. Let's get this word specific heat for a minute here. Specific is a weird old word in science. It means something like per unit mass. Specific. It doesn't come from like specific as in the opposite of general. It means specific as in for that species. In this case, the species is like water molecules. And the specific heat of water is how much heat the specific heat of any material is how much heat it takes to warm up 1 gram of that material by 1 degree Celsius. Turns out, most materials have a pretty low specific heat. A certain amount of heat will raise their temperature a great deal, whereas water has a very high specific heat. It takes a lot of heat to get even a small change in its temperature. But you knew that if you've ever been camping, right? I mean, if you build a campfire and you put a kettle of water on for coffee onto the campfire and you put some marshmallows on a stick over the campfire, you know that the same amount of heat, the heat's coming out of the fire going into the kettle of water and the marshmallow, but clearly the marshmallow is getting hot faster, right? Long before you have water hot enough to make coffee, your marshmallow will be hot and toasty and ready to be eaten. Marshmallow cream has a very low specific heat. It doesn't take very many calories. Oh, we'll get to that word in just a second. Calories are a unit of heat. It doesn't take very many calories of heat to increase the temperature of marshmallows compared to the number of calories it takes to increase the temperature of water. This is going to turn out to be hugely important. It's fundamental, though, to the nature of water. I'm going to put these Legos away before I spill them. There we go. This property of water is called the specific heat of water. It's the amount of heat it takes to change 1 gram of that material and increase it by 1 degree Celsius. And it happens to be how we define the unit of heat that is a calorie. Now, calorie, I know you're thinking about like when you eat a Twinkie, it has so many calories in it. That is a related term. It's the measure of the amount of energy that's available to you in your diet from that food. But don't get confused by that. Think of this as something completely different, okay? A calorie is just a unit of heat. And for water, it's 1 calorie per gram per degree Celsius. Every degree Celsius we increase the 1 gram of water is going to take 1 calorie of heat. And that's actually very, very high as specific heats go. If you can go to Wikipedia or any place online and look up specific heats of different material, then they're usually much smaller than 1 in terms of calories per gram. So you can do simple little problems using this idea of specific heats. Like we can talk about, like if we, up here in this white box at the top, if you have 1 gram of water that happens to have a temperature of 20 degrees Celsius, and you could somehow add 1 calorie of heat to it, with a microwave oven or on a burner or something like that, you end up with 1 gram of water with a temperature of 21 degrees, right? And in fact, you can do all kinds of problems that are only interesting in like a thermodynamics class, where you could talk about, well, what if there were 5 grams of water, or what if you added 10 calories, or what? Who cares? That's not where we're going with this. Where we're going with this is to talk about the specific heat of the material. So specific heat isn't like something that you, oh, look, this burner is giving off specific heat. No, specific heat is a number. It's a property of the material. In this case, the material is water, and as it happens, the specific heat of water is one of the highest in the universe. It takes an enormous amount of heat to change the temperature of water. But we're going to find out there's other things that even need more heat. Alright, well this isn't exactly, second grade science class. You already know that water occurs in 3 phases. It comes as a solid and a liquid and a gas. In fact, all of them are important in meteorology, right? I mean, snow and sleet and hail are all forms of ice, liquid water, rain, drizzle, there are forms of liquid water, and of course water vapor in the atmosphere will be a type of gas. In and of itself, that's not terribly exciting. What is exciting is the transitions from one phase to another. What actually is happening when we transition from a substance from one phase to another? That actually has all kinds of important meteorological consequences. I mean, you can already picture, for example, formation of a cloud. Formation of a cloud is going to require changing water vapor in the cloud into tiny little drops of liquid water. Okay? We're going to be condensing water vapor into liquid water drops. That's a phase transition. Okay? The word phase transition is probably new to you, but the idea, of course, is old hat. Now, what we're going to do is we're going to start with the easiest ones to think about first, and that's freezing and melting. Okay, freezing and melting are sort of the opposites of each other. Freezing is changing a substance from a liquid to a solid, and melting is changing something from a solid to a liquid. Okay, let's dispense with a misunderstanding about this first. It's often said that water freezes at 32 degrees Fahrenheit or 0 degrees Celsius, but strictly speaking, that's not exactly right. It is true the other way around. Ice always melts at 0 degrees Celsius, 32 degrees Fahrenheit, but it isn't always the case that liquid water will freeze at 32 degrees Fahrenheit. The issue has to do with impurities. If you were trying to get the water vapor, the liquid water molecules, well, wait a minute, what is freezing going to entail? We're going to need to take liquid water molecules, which are able to move around in the form of a liquid, and get them to line up into an ice crystal. That's going to turn out to be hard. But to think about why that would be hard, let's forget about water molecules for a minute, let's talk about kindergartners. Let's say we had a bunch of kindergartners, and they're running around like crazy maniacs, like kindergartners. If you wanted them to line up, are they going to do it on their own? It's actually going to be really hard to line them up. If you go and grab Jackson, and you put Jackson right here, there's always a Jackson in kindergarten, and then you go and grab Aiden, because there's always an Aiden, trust me, and you're going to put him up next to Jackson, where did Jackson go? He's already gone, okay? Getting them kindergartners to just line up is really hard. If you want the kindergartners to line up, every kindergarten teacher in the world knows you got to have like a line painted on the ground, and that's Jackson's spot, and that's Aiden's spot, and that's Taylor's spot, and they have to have a place to line up. Okay? In the same sort of way, if you have a sample of just pure liquid water, and the water molecules are moving around, and you're cooling them down, and they're moving slower and slower, but you want them to stop moving and line up into a crystal. Okay, here's my first water molecule. You stop. You're the first one of my ice crystal. Now here comes the next one. I'm going to put you right here. You're next to it. Where'd that first one go? He's gone already. It turns out it's really hard to get pure water to freeze. It needs to have some kind of impurities in it. Dust, pollen, different kinds of materials that are going to be in any kind of sample of water. Because they'll have like crystal structures and so on that like the very first water molecule can freeze onto, and then the next one can line up next to that, and the next one can line up to that, and you can start growing an ice crystal on that impurity. Alright? But, well, what if there aren't any impurities in there? Well, then you can get what's going to be called supercooled water. Supercooled water is liquid water at temperatures below 0 degrees Celsius, 32 degrees Fahrenheit. That's going to be hugely important in a couple lectures when we are talking about cloud formation and precipitation formation and so on. But it turns out those kind of impurities aren't exactly rare. The kind of impurities in a sample of water that will allow an ice crystal to grow, as long as you have more than like a drop of water, odds are there's already impurities in it and you just don't need to worry about it. Though you'll have the kind of impurities you need in order to avoid the whole issue of supercooled water. When you fill up the ice tray in your refrigerator and you make ice cubes, that sample of water that's going to become an ice cube is large enough. There's, no matter how well you filtered it or anything, there's some impurities in it, and you'll freeze at 32 degrees Fahrenheit. Alright, so we have this idea of freezing. Our water molecules had some energy, they were moving around, and we want them to stop doing that and line up and form a crystal. All right. But I kind of gave a little bit of the secret away here. The molecules had some energy. The water molecules, when they were a liquid, had some energy and were moving around. And we were cooling them down towards 0 degrees Celsius. And at 0 degrees Celsius, something's going to happen and we're going to make them stop doing that moving around. But what if there's water and ice together? Anytime, like in this beverage right here, anytime you have water and ice together, it's a very specific temperature. It's 0 degrees Celsius, 32 degrees Fahrenheit. Because here's the deal. If it were any colder than 32 degrees Fahrenheit, all the liquid water would have turned into ice. If it were any warmer than 32 degrees Fahrenheit, all the ice would have turned into liquid water. Anytime you have liquid and ice together, the temperature is exactly 32 degrees Celsius. Now that's going to turn out, 30 degrees Fahrenheit, 0 degrees Celsius. That's going to have meteorological importance later in this semester. But for now, I want to talk about that cup of ice water right there. What is actually going to happen if I take that cup of ice water and I do something to start heating it up? Like I set it on a burner, or I set it out in the sun, or I hold it with my hot little hand. Okay, my hand is warm. By conduction, it's putting heat into, calories of heat are coming out of my hand and into that cold cup of water. What's going to happen with that cup of water? Well, to understand this, I want to watch another one of these flash animations that I have made. Again, I made these quite a few years ago now, but they work really quite well. You can, by the way, from the PowerPoint, you can actually go to this this website that I keep up here and watch them yourself and read the text and so on. But I've also captured it here on the screen. The ice cubes and the liquid water that I have animated here are at the same temperature. Those molecules that are moving around in the form of liquid water have a certain amount of energy. They're moving around at a certain speed. If we do the math or measure it with a thermometer, it works out to 0 degrees Celsius. Same with the molecules that are there in those ice crystals. Yeah, they're not dashing around all over the place, but they're just moving around a little bit. But because they're packed in there in that tight little ice crystal, even that little bit of moving around is frankly a lot of energy. Kind of like when I had the Lego box. Even a little bit of moving around of the Legos in that little Lego airplane would have taken a whole lot of energy. So both that liquid water and the ice crystals are 0 degrees Celsius. Every now and then, one of those liquid water molecules hits the ice crystal molecules. And just like a cue ball on a pool table hitting the rack of pool balls when you break at the beginning of a pool game, sometimes it transfers that water molecule, that liquid molecule, transfers energy into the ice crystals and breaks some of them loose. Some of the energy from the molecule moving around in the form of liquid is transferred into the molecule that was in the ice and busts it loose from the ice crystal. It can now move around. It has joined the liquid. It has melted. But look what that means. That means energy that the liquid molecules used to have got used. Energy that it had got used to change the ice into a liquid. To give that molecule that was just sort of wiggling there in the form of the ice enough energy to leave the ice and go become liquid water. This is an interesting phenomenon. We add heat to the liquid water. When I hold a glass of ice water, my hand is putting heat into the cup. But there's still ice and still liquid water in there. Clearly the cup is still 0 degrees Celsius, 32 degrees Fahrenheit. Where did all that heat go? If I put a cup with ice water onto a burner, I add heat with the burner, but the temperature is still ice and it's still liquid water. Where's the heat going? I put it into the microwave. I start heating it up. There might be less ice than there was before, but it's still ice plus water. Ice plus water is always exactly 0 degrees Celsius. Where did that heat go? Oh, this was an ugly mess in the history of science. It took a long time for them to figure out that what happens is called, that there is an absorption of latent heat. But before we explain what that is, let me, just like I told you about specific, let me tell you about latent, because latent is another one of those creepy old words in science. And this is going to be a term that we're going to use in every module for the rest of the course. Latent heat, latent. When I used to teach this class face-to-face with students, I would usually find some poor soul hiding in the back of the room, and I'd go, "This is Bob," or whatever his name was. "Bob has a latent desire to kill his roommate." What does that mean? Okay, now, poor Bob would be dying of embarrassment, especially if it turns out Bob's roommate is also in the class. But here's the deal. What does latent mean in that sense? Does that mean Bob's going around telling everybody he's going to kill his roommate? No, no, no. It means it's hidden. It's a dark secret, and we're not letting anybody know it's there. Latent. It's a creepy old word, but it describes what's going on with this heat in a little bit. Heat is being hidden. Heat is being hidden in the fact that we have taken real heat that we could measure before is being taken out of the system and being used to change the ice into liquid water. That heat is still there, but it's hidden. It's hidden in the fact, I mean, the temperature didn't go up. It's still 0 degrees Celsius in that cup, right? But we've added heat. It's just been hidden. It's now latent. It's hidden in the fact that we have changed some of the ice into liquid water. And this was a huge problem in the history of science. Oh man, the old dead white guys of science hated this problem. They would get together with their, and be stroking their beards, and they would get Mr. Daniel Faraday's, I'm sorry, Fahrenheit's new invention, the thermometer. Daniel Fahrenheit's the guy who invented the thermometer. And they'd be measuring, and they would have a beaker of water with ice in it, and then they would put it over the burner, and they were sure that that should make the temperature go up. And it doesn't. Because the heat isn't being used to increase the temperature until all the ice is gone. At first, heat is being added to the ice water, but the heat's only being used to change the ice into liquid water. Once it's all water and you keep adding heat to it, then the temperature goes up, and at a very well understood rate. The specific heat of water. For every gram of water that you have, you add 1 calorie, and you get 1 degree Celsius of increase in temperature. But man, the old dead white guys of science were puzzled about this. It was a really embarrassing long time before they figured out this whole business of latent heat. The heat is hidden. It's very real. Hey, the word isn't on the slide here, but a good word to know that is the opposite of latent heat is sensible heat. Not sensible, well, it sounds like the word is sensible as in like it has a good head on its shoulders, but it means sensible as in it can be measured, it can be sensed, it can be felt. The kind of heat that, like, you put your hand into a cup of hot water and you sense it, is sensible heat. We add sensible heat to the water and the cup with the ice on it. I mean, if you put your hand by the burner, it's hot. Sensible heat. But somehow or other, that sensible heat is being hidden. It's being hidden in the fact that we changed ice into liquid water. And in fact, this happens at a very specific rate. It is 80 calories per gram. It takes 80 calories of heat from the environment, the surroundings around the ice and the water, to change 1 gram of ice with a temperature of 0 degrees Celsius into 1 gram of liquid water with a temperature of 0 degrees Celsius. So I have that spelled out there, the white box at the top of the screen. So 1 gram of ice, that's 0 degrees Celsius, add 80 calories of heat, which is a hell of a lot of heat, and you get 1 gram of liquid water that's still 0 degrees Celsius. We haven't actually made the water any sensibly warmer, but heat is hidden. It's hidden in the fact that the water molecules aren't just sort of stuck in ice anymore, they're moving around. Just to show you how much heat 80 calories is, 1 gram of liquid water at 0 degrees Celsius, if you add another 80 calories to it, you get a gram of water at 80 degrees Celsius. 80 degrees Celsius is almost boiling. That is a huge amount of heat. So melting the ice absorbs heat from around it. It's why when you use your hand, which is warm, and you hold the cup feels cold to you, because heat from your hand is being absorbed. Sensible heat in your warm little hand is being absorbed and hidden, becoming latent, in the fact that we are converting ice molecules into liquid water molecules. Ice doesn't keep your drink cold because it's cold. Ice keeps your drink cold because it melts. And we used to, in the classroom, actually do demonstrations that illustrated this. We would use like nuts and bolts. Okay, if you have a cup of water and you have some nuts and bolts that you used to have, you kept them in a cooler or something like that so they're cold, you put the nuts and bolts in your drink, it seems like it would keep your drink cold. But it doesn't. Okay? Right away, as you hold the cup and heat goes from your hand into the cup, it increases the temperature of the nuts and bolts, and it increases the temperature of the water, and the temperature goes up. Ice keeps the drink cold by absorbing the heat from the environment around it and making it latent in the fact that we have converted ice into liquid water. Because of this, we have a confusing terminology. We would describe the process of melting as being an example of a cooling process. Melting is a cooling process. Write that down. Melting is, pause the video, melting is a cooling process. What do we mean by a cooling process? That means it is absorbing heat from the environment around it, from its surroundings. When you hold the cold cup and ice is melting in that cup, your hand gets cold. Heat is being absorbed from your hand into the ice water system. And the latent heat of melting ice is a big number. It's 80 calories per gram. Every gram of ice takes 80 calories to make it melt. Now, I told you earlier in the lecture, melting and freezing are opposites, right? If melting is changing ice into liquid water, freezing is changing liquid water to ice. So if melting was a cooling process and it absorbed heat from its environment, freezing must be a warming process and it releases heat. Wait a minute, oh my goodness, well, hold on, we don't like that. Freezing is a warming process. Huh. Well, it's actually not so hard to think about once you realize what we're talking about here. Well, freezing means that we take liquid molecules that are moving around, they've got energy, they're doing their thing, and we got to get them to stop moving. Sit still. Line up in a crystal. That involves letting energy out. Those molecules have to give energy off, and that releases energy into the environment. It is a warming process. As liquid water freezes into ice, it gives that heat off into the surroundings around it. And it does it at, perhaps not surprisingly, a rate of 80 calories per gram. Every gram of liquid water that you turn into ice involves releasing a whopping 80 calories of heat into the surroundings around it. In other words, if you take 1 gram of liquid water at zero, like I have in this box here, if you take 1 gram of liquid water with a temperature of 0 degrees Celsius, you can make it become 1 gram of ice at 0 degrees Celsius, and you get 80 calories to release into the environment. Now, you would be a perfectly normal, unhappy student if you said that can't be right. How could freezing be a warming process? Doesn't sound right, does it? I agree, doesn't sound right. But let's picture what's actually happening when you freeze something in your freezer. When it's warm inside your freezer, the freezer kicks in and the engine runs, the compressor runs, and all that kind of stuff. That's how you know something is warm in the freezer, right? And it needs to be cooled off. If you put a glass of water into the freezer, like in an ice cube tray or something like that, and you close the door, listen, shortly the compressor will kick in. The thermostat inside the freezer says things are warming up in there and they have to run to do work. Why is that? Why is it getting warmer inside the freezer? Because you put a cup of water in there, or you put an ice cube tray in there full of liquid water, and as it's freezing, every gram of water that you just put in is giving off, is emitting to the environment, is releasing to the environment 80 calories of heat. That 80 calories of heat was latent heat, hidden in the fact that it was liquid water. Hidden in just the reality of, hey, these molecules are moving around. When they stop moving, they have to give that heat off in the form of sensible heat, which in the case of the freezer, it has to get rid of by running the compressor and all the good stuff, and I can't remember exactly how a freezer exactly all works. Cool. Now you have a diagram very much like this, except I've hidden parts of the diagram, fuzzed it out a little bit. You have a diagram very much like this in your book, where we're going to be talking about the 3 phases of water, solid, liquid, and gas, and we're going to be talking about the transitions between those phases, and you can see already we've talked about 2 of those transitions, melting and freezing. You can see how the red arrow shows us melting goes from solid to liquid, and it absorbs heat from the environment when that happens. It is a cooling process. It takes heat away from its surroundings, and I don't like how it says 80 calories. Let's say 80 calories per gram. That's more correct. I think the caption for this video really only said all numbers are per gram or something. In the same way, that blue arrow there shows the transition from liquid water to solid ice, and it is releasing heat. It is a warming process at a rate of 80 calories per gram of ice you're making. Now, in the rest of this lecture, we're going to build the rest of this diagram here to help fill in all the details as to how this works. But before we get too much farther with this difficult issue, let's answer 3 quick questions. Question 1. How much heat is 1 calorie? Is it A, enough to increase the temperature of 1 gram of water by 1 degree Celsius? Is it B, enough to melt 1 gram of ice into liquid water? Is it C, enough to freeze 1 gram of liquid water into ice? Or is it D, trick question, calorie isn't a unit of heat? All right. Make a choice for those 4 options, get a little feedback before we move on to question 2.